right. The thing about me is that I really think that I'm a nobody, and that sounds really good, but like I say sometimes, yes, I'm Dr. Tandy. I've had an opportunity now to architect two well-funded space stations, but if you need me, I'll be cleaning toilets. That's really the way I think about myself. A little bit about me. I got my bachelor's and master's in structures at the University of Texas in Austin. I joined Ball Aerospace and got to do the mirrors for the Pluto mission. So I have a lot of pride. When those photons came back, I could say those came off my mirrors. I worked with the OMS program. This was measuring ozones, lots of remote sensing instruments in my career. And then somehow, I got lucky and started being asked to take on large structures. So this is James Webb Space Telescope. This black structure in the center, you can imagine the whole thing. This is actually called the aft optics bench. It's got two mirrors in there. And Kristen Martinez was the design lead, but I was her structural analyst lead. And together we optimized and designed that structure. So again, a lot of pride when those pictures are coming back now, that they're bouncing off that work. From there, I joined a program called MORE. This was supposed to be a 100-meter long telescope with a 20-meter aperture. It was funded by DARPA, which is the US Defense Agency. And we worked on a Fresnel lens, so we needed a long focal length because just a little bit of refraction. And we built a 5-meter thing. And from here, I went on to other large structures. And then I reinvented myself. And this is kind of, I think, some of the themes of the Iteration conference. I had a background in computer science, and people said, hey, you've done all the structures work, and you've done a lot of that by automating things and writing programs to kind of create new tools for yourself. And so could you do that for us? Could you come and write some flight software for this sea surface temperature instrument? That sounded like a good time. They said, hey, you wrote the code and you've done the structure. Why don't you get in the airplane and fly with it? And so I was able to do that, join the Airborne Operations Group, and had 1,000 hours of hands-on time with instruments all over North America. Eventually settled on this methane monitor. This is a dual frequency LiDAR system, and we would fly in an airplane, and you could detect methane coming from the factories and the pipelines and the wells. And I was so convinced that that was going to be the rest of my life that I went back and got a PhD when I was 36 in that technology. And then they pulled the rug out and said, we're not doing that anymore. So then I had to reinvent myself again. We went and did CubeSats. But because I had all this background doing research and structures and hands-on, they said, why don't you learn to become a mission architect? And one of the things I did was mission architect methane sat, which is from the Environmental Defense Fund. And it flies around, it's a spectrometer, and it measures methane from the countries that won't let us go in there, like Russia. Russia says that they have this much methane coming out. How much do they actually have coming out? So I'd really built my career. I was heading somewhere, and I gave it all up, left the space industry, and started a cross-stitching company. Total left turn reinventing, and so you can actually get this app still. It helps people put their ideas down. It says, I want to create this needlepoint, I want to create this sewing kit, and I was like, well, I'm going to help you do that. But I miss space too much. And I learned a lot. You have to find your team when you start a company. I know there are a lot of entrepreneurs out there. And finding your team, I think, is rule number one. I never found my team, even though I had three different startups in that period. Came back to space, joined Blue Origin, and I became the senior manager of all the architects at Blue Origin in the Advanced Concepts division. As part of that, I worked on the Blue Moon program. Very proud of that work. We didn't win, we lost to SpaceX, but the team did really good work. I had a good time doing that, but after that failed, or it didn't go forward for us, it was time for us to start creating a space station, and I was tapped for that effort. And it was me and 4 part-time junior engineers to start. And within 7 months, we had won $130 million from NASA. There are a lot of things that I love about this. I have to give some credit to others, even though I was the technical lead for the program. A lot of these beautiful renders and vision comes from Jeffrey Montes. He was a classically trained architect, like a building architect who joined the space industry, and so you can see a lot of that influence. Clearly, an engineer has not done this, right? An engineer like me said, well, I need 60 kilowatts of power, and you have to have so much thermal rejection. And yes, you created a beautiful vision, but it's not going to work, so let's get something that does work. There's a lot of that iteration. Internally, so we had another architect, Makoto Air, is the kind of the visionary architect for the internals here. But again, we're trying to create new spaces. You can kind of see this concept. We want free and floating and big. And this was a really good time. I had a great time at Blue Origin. And right after we won that $130 million, I thought, I can see where this is headed. We're going to grow to 2,000 people, 3,000 people. This is going to be a huge program. But I still had this bug. I wanted to be an entrepreneur. And that's where Gravitics comes in. I left Blue Origin without a plan to join Gravitics, but then was able to stumble into that company and was hired on as their chief engineer. So I'll talk a little bit more about this in a little bit, but this is our massive StarMax volume that you can use to live in or run data servers or MMA fights or whatever you can think of that you want to do in space in a huge volume. Okay, so how do you design a space station? Well, there isn't really a textbook, right? So how many space stations have existed in all the decades we've been in space? Not that many. And so every time you do it, you have to go back and learn from the very smart people before us. This is Skylab. This was actually, it was a space station, technically, but it was really one module that was launched up. And that's this part here. It was kind of one big monolithic thing that came up on the old Saturn V rockets. This is actually a telescope, this structure up here. And then they would come in with their command module. And it was great for what it was. The first kind of true space station was a Russian Mir. And I'm using that definition to say that something that was assembled over multiple launches. And their concept here was a central kind of node with a bunch of docking ports. You can see it up here. There, kind of plugging in, and down here, kind of plugged in. If this looks pretty haphazard and a little bit chaotic, that's because it was. Very smart, but they didn't have a lot of good tools, and so you can kind of see what happens is they have radiators and solar panels going every which direction. It turns out that even at 400 and 500 kilometers above the Earth, there's a lot of drag, so they had control issues. One thing you don't see are windows, right? They're tiny little windows, and the astronauts reported getting depressed because they were basically stuck in a very loud, very noisy, very smelly environment. It leaked all the time, fluids everywhere, and you could only see Earth through just a little tiny porthole. NASA said, we're gonna do better, and we have the space shuttle so we can launch whatever, Livingston probably has a number. We're gonna launch 100 times a year. And so they had big ambitions. This was the first one. There's this great gravity gradient concept. So here at sea level, I weigh so many kilos. And if I go to Mount Everest, I weigh a little bit fewer kilos. Same thing is happening in space. We build something really tall, and it naturally wants to stay vertical. So they put all the people at the bottom, very noisy. They create a lot of vibrations. And they put the delicate sensors at the top. Turns out, though, like a guitar string, if you tweak it down here, you would tweak it up there. And so they said, all right, well, we have the space shuttle again, so why not just build it twice as big? So they have two vertical things, and they put some crossbars in there, and then a horizontal thing to put the energy out to the side. But around this time, they started figuring out the space shuttle was not actually going to bring as much to space as they thought, as often as they had hoped for. All right, so side note, NASA had to go back to the drawing board. So this is a picture of Bruce McCandless. You've probably seen this at some point in your life. So here's the thought experiment. If we are looking at Bruce, and he's flying backwards, so he's kind of flying this way into his orbit, and you have a wrench, and you want to throw it to Bruce, how would you do it? It turns out, with orbital dynamics, that one way to do it is to throw it straight down. That's because if you tell me your velocity, I will tell you your altitude. So if I'm going this speed, and I put a wrench down, it's going to keep going the same speed, but it wants to come back up the altitude that that speed sets. So you throw it down. It has the inside track because it's closer to the Earth. It's going to move forward, but it's going to elevate at the same time, and Bruce can catch it. If we reverse directions, if now we're going backwards while Bruce comes to us, we reverse the order. Throw it straight up. It wants to come back down, but it's on the outside track, and Bruce will be able to run into it and catch it. Another kind of thing that happens is it's very difficult in space to fly these parallel formations. You can imagine, airplanes flying next to each other. Very hard to do that in space. If you start out on the left side, then over time, the course of one orbit, you'll actually translate through Bruce to this side, and then come back through Bruce to the left side. This picture got a little bit cut off here, but you can kind of see what's happening is that we are all orbiting around a center of mass in the Earth. And so if you start out on the left side, if you're the blue line, then you actually cross through a center point, and you come out to the right side, and then back again. So all this matters because of the way you want to dock with the space station. If you imagine that we're flying into the screen, the best docking operation is really at the same plane as the space station. Pretty good docking operations. You come underneath, lift yourself up, and dock. The zenith, or the top, is decent. One reason that we don't like to dock up there is because you have to translate through here. And I know there are people here from clear space talking about orbital debris. That's a problem. When you translate above, you're creating paint chips, little bits of foil, MLI, maybe little chunks of ice, and now the space station can run into that. So although you can, it's favorable from orbital docking operations, you try not to do it. And then, because you can't really go docking from the side, you can, but if your thruster breaks, which has happened a few times, you'll run into each other. So we put our radiators out there. Okay, and so that's the space station, right? So now when you look at it, you can see they've docked here in the center at the mid-plane. They've docked from nadir. Zenith is looking pretty clear. They have docked up here a few times, I think. But generally, over the whole decades that it's been operating, I think maybe 3 times. And then on the left and right, they have their solar panels. These white things are the radiators. They have some more radiators here. Now, NASA spent billions and many, many years figuring out the optimum design station. And China was like, well, thank you very much. I mean, they're smart people, too. But you can see what they've done. They've put their energy in and out on the left and right. They're docking from underneath. Over here, they're using ion thrusters to fight the drag. I didn't talk about drag, but that is a big issue. And on the right-hand side, you can see they have some docking operations. So space stations sound like a solved problem at this point. You just need to put your things in there. Well, it turns out, if I go back, that this is super cool, and I will always respect the NASA people who put this together and their partners. It's a very loud place to be. Very small volumes, meaning the very small airflow ducts. Actually, astronauts wear earplugs 90+% of the time, and some of them have lost permanent hearing from being up there. It can get stuffy, oxygen levels, difficult to maintain. A lot of them report headaches because there's too much CO2. Not enough storage volume. When you open up your Christmas presents, you get wrapping paper everywhere, and now you need a big trash bag to hold that trash. Same thing happens. They bring up all these supplies. They're packed so nice and neat inside the module, and the astronauts open them, trash everywhere. And so sometimes they've actually blocked their own ventilation from all this trash that they don't have enough volume to put it into. So what we're saying at Gravitics is not that we need to reinvent the space station. This is a brilliant, beautiful design. What we need is more volume. So this is what's going on here. This is the Japanese module. Japan should be very proud of this. This is a beautiful machine. It's about 4.4 meters tall, about 11 meters long, and it has 155 cubic meters of volume. We are about the same length, but we are 8 meters in diameter, and that gives us 400 cubic meters of volume. This is a photo that we took a week or two ago. This is the factory that we're building out, and our artist has put in a couple things here. Here's the Japanese module, and here's a concept. Because this is something that we're putting together for a conference, it doesn't have the bottom dome, so this is actually much bigger. But you can see the people for scale on the truck. And you can imagine that once you put in your experiments and your payloads and your environmental control systems, you're really left with a small area in the center. And so that a lot of times you'll see the astronaut videos when they're flying like Superman or Superwoman right down the middle. This is a completely different experience. You can see a person in here for scale. You can imagine, even with racks in here, how much more volume. And when there's larger volume, there's larger air ducts, it's quieter. You can hide the things that normally would trap people, cables and wires coming around. All right, enough advertising. I've got 4 big problems as we set up this company. First, and I haven't talked with many of you about this, but I would not be surprised if it's hard for you to find really good designers and analysts. It's my experience that we make it worse. Systems engineering, very important. I'm about to bash systems engineering. So let me say in front that it is important, we must have it. But I've found that systems engineers tend to build these pyramids of themselves. You got your junior systems and your mid-level, and at the top are all your senior systems engineers. But all the people who are actually doing the design and analysis work are milling around the outside. They're not included in this structure. And they find, and I'm speaking from my personal experience, is that you do all this work, you stay up late running your Nash-Tran models and your numerical simulations, and you tell them this picture says green is good and red is bad, and then they make the decision. And sometimes you don't agree with it because you're like, look, red is bad, don't do that. And they say, well, I know better than you. And they guard the big picture. They have their tools, and you're not allowed access to their tools. And so a lot of times you don't know what's happening in the big picture, but they'll say, don't worry, I've got it. They stay through the whole program. If you're a thermal engineer, they want you to design that awesome radiator and then get the hell off their program, right? You're expensive. You've got to get out of there. But the system engineers, they get to stay the whole way. That means they go to the public events. When you go to a launch campaign to watch the rocket go off, it's 80, 90% system engineers and program managers. And the people who actually designed and built the hardware have been off the program for years. And then they have the audacity to be like, I'm working so hard, I'm on the program, I'm making all the decisions, I should pay myself 20, 40, 60,000 a year more. Plus, I should be part of a bonus program. So that if I figure out how to get that thermal engineer off 2 weeks earlier, I should get that money. So why would anyone want to be just a designer analyst? I think, this is my personal opinion, we've got to figure out how to invert that. Systems engineers should be the trunk and the branches connecting things, but we have got to start lifting the designers and analysts into the light. We have to make them feel, because it's true, that they are absolutely critical to any successful programming company. We still need to talk interfaces. I mean, branches are connecting leaves, right? And there are going to be storms in a company, in a program, so you need the tree to be flexible but strong. And that's why system engineers are important. But we've got to start inverting that pyramid and making people feel like you can have a real career being an awesome expert for decades. Second problem we have, better knowledge transfer tools. Bill's opinion, again, stashing Word documents has set us back. Ben talked a little bit about this, about sharing information in Word and Excel. In my experience, again, you write these reports, you give it a title, you put it in some data management system, and nobody can find it ever again, unless you know the exact title. And then you have someone you're trying to train, you're like, go find that document, I think it's this title. Maybe they find it, but they're not natively finding it, they're not organically finding it. This was a big one for us. I worked with a mentor, Tony Dreher. If I needed an epoxy materials property, I'd say, Tony, what do you have? He'd go to his filing cabinet. second drawer, 38th folder. He just knew in his mind, he'd mapped his whole filing cabinet and he handed it to you. That doesn't happen now. And then somehow we need to start putting learning into the documentation. We're bringing in these new people, we call them fresh out of university. Somehow we need to not just say, these are the numbers, we need to say, these are the why behind the numbers. And I want to find a way to put that documentation and learning together into one thing. I have a few things, but I really have a big question mark, and that's one of the reasons I'm here, is to try to learn from all of you, how to do that. I do like Confluence, Blue Origin. I would not let people write Word documents. I would say, if you're gonna do a report, put it in the wiki page. And I want you to link it, and that's the requirement. And over time, we built up all sorts of pages about ion engines, batteries, solar panels, parametric plots. And it became so useful to our program that people outside of other programs started mining our own data to solve their space problems. When I write code, when I work with software developers, I say, I want you to write your comments before you write your code. I want to know not only what those next 3 or 4 lines are going to be doing, but I want to know why they're being done. And if you're using any references, Stack Overflow, if there's any programmers out here, Stack Overflow is your main source. I want that link in the code comments. Then, like I said, I run out of ideas. The third problem, schedules. Fill in the blank. Why do we do this to ourselves, right? Why do you have to have a schedule? And it's ironic because it's like lies built on lies, and people get mad at you because the lies are not audacious enough, right? You go around, you do your job, you salute and say, I'm gonna build a schedule, and you interview people, and you get your metrics, and you put it together, and you deliver it to the boss, and they say, well, it's too much time, take 3 months out. Like, your lies have got to be stronger. And then I know there are managers out here, when you ask how long is it going to take you and they give you a number, you're like, well, they've got 2 years of experience. I'm multiplying by 3. So you want people, you ask people for things and then you don't even believe them. And then probably from a manager's experience too, it doesn't really change experience. If you're at a startup and you're working 40, 50, 60 hours and someone tells you, well, you missed the deadline on Tuesday, they're going to be, what was I going to do? I'm already working hard. So what does it matter, right? So, and this is, I do a lot of hiking, a lot of traveling and adventuring. You have a start point and a finish point, but when you're out in the woods with no map, you're making what are called beelines. That's what we call them in the US anyway. You find a tree, it's about 50 meters away, and it's more or less in the direction you want to go, and you go to that tree. And you get to that tree and you say, all right, there's a boulder, 100 meters, I'm just going to go straight there. And you're not plotting the steps in between. You may have to rappel, you may have to climb a wall, but you're not plotting all that 4 steps ahead. You're looking for the next target, moving ahead. This is the way humans think, in my experience. But then we use Microsoft Project and Gantt charts as if it's a straight line with knowable infinite steps. The way I like to put things together is understand what the deliverable deadlines are, create those beeline points, create design analysis cycles. This is part of the agile methodology from software. And then plan in detail no more than a couple. We may have to do some rappelling, and we'll bring our rope with us when we have to get there. But we're not going to be planning the entire cycle 2 years from now because you don't know who you're even going to have. That person may leave. You may have 10 more people. How can you possibly know, and why are we going to spend a lot of time on this? And then, again, my personal opinion, preference is to resource load to products, not steps. People say, I want to build a radiator in space, and I need to do this step, this step, this step, and that's going to take 4 hours, and that's going to take 12 hours. You can't possibly know that. You just need to understand that a radiator takes about 3 months, and then resource load to the product, not the step. Fourth problem. Programs never develop in straight lines, but we make and use tools as if they do. Here's an example in the space industry. It probably has it in other industries. You have this requirements review where everyone sits around and says, all right, we've got 2,300 requirements. Is that enough? Have we done the job? Yes, okay, let's pat ourselves on the back. Now, with those requirements, we do the architecture review. Your solar panels are going to go here. Your radiator is going to go here. And you have all these swim lanes And the swimming pool just stops at these points, and everyone gets to the same page, and they move on. In my experience, I call this the spiral of receding chaos. This is the way programs really develop. You think you know what you're doing, and someone says, well, it turns out that the radiation environment is way worse than we thought, and if you use stainless steel, you're gonna have secondary radiation effects, so now you're gonna use aluminum instead. Well, there went all your requirements from your requirements review. And you come down here and you say, well, you're gonna weld that aluminum, but you chose a lithium aluminum, and it turns out that's very hard to weld, so you need to go to something without the lithium. And now your requirements and your tooling changes again, and you're constantly getting bombarded by reality. I call it getting punched in the face by reality. But I have never found good tools for this. Programs, let me go back. The programs run like this, but the subassemblies run like this too. Your radiator, your solar panels, everyone building anything has their own spiral of receding chaos. It's like a swarm of bees in the American Southwest. If you've ever seen a swarm of bees, it's very loud. It's like a helicopter or an airplane buzzing you. And any single bee, all over the place, but that swarm going somewhere with purpose. Programs are filled with these spirals of chaos. You can imagine a big one, but 1,000 little ones. And some of these spirals are really long, and some of them are very short, but we don't make tools that design to that. All right, so I've listed 4 problems about giving good solutions. To quote the internet, that's why we're here. So I do have a few B lines. First, invest in people, to echo what Livingston and Ben have said already. Give them responsibility. Don't tell them you're a thermal engineer and you can only do thermal analysis. Give them some of that systems engineering responsibility. Let them design some of the electrical stuff if they're inspired to. Share the sunshine. It's a little bit ironic because I'm the chief engineer and I'm here talking to you instead of one of my people, but I promise that we do try to lift them up and give them a lot of the limelight. Work at the speed of trust. I'm a big one on this. This is a book by Stephen R. Covey, Speed of Trust. If you've never read this book, I highly recommend it. But I hate when people put things behind passwords because all it does is slow down your company. I'm of the opinion that it's not the information that's important, it's the execution. I could give you everything you ever wanted to know about Star Max or Orbital Reef, and it would not matter to you because A, you don't have Jeff Bezos' money, but B, even if you did, you don't have the team and you don't have the infrastructure and the knowledge to actually put those things into place. So why do we keep handicapping ourselves by hiding our information as if it's some sort of secret? Number 2, minimize rigid configuration control. Ben talked about change management. I'm actually against a lot of change management. I prefer something like Confluence or Box or any of these other kind of modern tools that when you put a new version in, it says, all right, that's version 28 or version 32. If you don't like what your employee did at version 48, go back to version 47 and stop telling people that they cannot add new information to the repository unless they get somebody to peer review it. Let's move a little bit faster and let's keep moving forward. Good communication takes time. I spent a lot of time one-on-one training people, and that means I work long days, but it pays off because you're building trust, you're building communication, you're helping people understand where they fit in the big picture. I think that people underestimate how long it really takes to have good communication. And then this is my final slide, that be comfortable with chaos but not satisfied by it. This is kind of one of my personal mottos. I don't know where this quote came from. I did not come up with it, but I couldn't find a source for it either. But we have to be okay not knowing sometimes. But if you have that beeline point, it'll be okay. All right, that's it for my presentation.
Thanks, Bill. That was great. And you talked about not being able to walk in a straight line. And look, if you're anything like me after a few Friday after work drinks, then yeah, you'll know that's definitely true. But now for some questions. Anybody here with something to ask?
You talked about knowledge transfer being really, really important and how like Confluence and things like this are more important. What's the most effective way of not transferring knowledge in that medium? Is it reports? Is it like analysis? Is it some simulations people can run? What, in your experience, is the best way of doing that?
Yeah, that's a great question because I think the TikTok generation, you want information fast, right? If you put it in a Word document or even on a Confluence page and there's 5,000 words, I mean, my eyes glaze over. I have a hard time. I need pictures. I want that green is good, red is bad. The challenge is that creating a media product that would be more useful takes time. And so I would love to find a tool, and we have done this in the past in other companies I've been in, where you record yourself sharing the information and posting it, but that's data intensive. I think this is an area where we need better tool set, to be honest.
Well, just to follow up on that question, how do you incentivize engineers to actually report or log that knowledge learned? Because when you are just crunching numbers and you need to deliver something, that might just pass by easily, right?
I've been really fortunate that I've also been their boss writing performance reviews. So they're de-incentivized not to do it. More seriously, I think that once you start creating that culture, people really get into it. As I mentioned, when we did it on Orbital Reef, we had page after page of all this great engineering information that wasn't just information, but plots that said, if you want this much power, this is the area of your solar panels, this is the mass, this is going to be your efficiency loss. That became so useful to people that they started adopting it for themselves and just saying, taking that as a cost of doing the right thing.
Hi, thanks. Great presentation. My question is, you spoke about the interfaces that systems engineers need to do with the design and analysts. What about with the rest of the team? So what is the responsibility that the systems engineers need to have relating with business, with marketing, with the rest of the company itself?
Another great question. I think one of the challenges of defining systems engineering is it's this massive, huge umbrella. You call yourself a systems engineer, you could be working with software and never see hardware. You could be doing business management and not even know really what's happening at the technical level at all. And so it's a little bit tricky, but I would say that to me, the systems engineering role is to try to keep the company out of trouble and organize things. Most accidents with space hardware happen at the interface, either the information interface or the hardware interface. So I think in Bill's opinion, I'm standing on my soapbox here, is that their first and most important job is to track the interfaces and make sure that people are talking with each other.
I was a little bit trying to follow your thing on resourcing, and I'm wondering, you said don't resource for steps, but resource for products, right? How do you do that? I mean, if you are building something that wasn't built before, how can you resource? And how do you sell your argumentation to the people that need to give you the resource to resource? If you understand what I mean.
It's a total chicken and egg problem, right? Which comes first? I think that's why you start a company with people who know, who have a kind of an understanding, who have done it before, because you're right, you have to know a radiator takes 3 months, and a structure is going to take so much depending on how much mass it is. And I think that's kind of the job of leadership, to be tracking those metrics. And unfortunately, if you went to Boeing or Lockheed, they have those metrics, but they don't share them. And so there's, again, no textbook from it. So sometimes you do have to do it at the step level, but I think what really gets me agitated is when I see people come back with things that are, well, this is going to take me 4 hours or 12 hours, when you should be talking days and weeks. Talk to the product level, you know. Yeah, sorry, the answer is, yeah, you just have to know the answer. I don't know. How hard could it be?
We're all learning in some way.
I think that the thing that I always want to impress with junior engineers that come in and they say, I'm going to do everything. I'm going to be an electrical engineer and thermal engineer and software, and they just feel like they're ready to tackle everything. But the challenge is you just don't know sometimes. People want to have control and own things, and they say, you know, the tighter you squeeze, the more things squeeze out from between your fingers. And so sometimes you just have to let go and let things take the shape they're going to take. It wasn't really part of your question, but the thought came out.
I loved your spiral model where it's not a line, it's a spiral, right? Like you come back to certain points that you have been before partially, but you're a step ahead. how do you, like, how do you in your daily work make people embrace that, right? Because if you it's the first step to have the understanding that it's not a straight line, but you were talking about that change management is the thing that you have to give people as a, like, as a core value. It is good to see change. It's good that you learn new information on the way. It's good that you are a step ahead. How you bring that into people's heads and into their actions.
I had a slide and I deleted it just before I sent it, but it was asking those exact questions because I don't have the answers. Because if you go to a venture capitalist and say, well, you know, we're going to be back at the same place we were 6 months ago, but smarter, they're not going to give you the money, right? You need to tell them, going back to the lies, you need to tell them you have a plan and it's going to be 3 months and it's going to be this way and then we're just going to hit these milestones and we'll never go back. And somehow we need a culture change that says, let's acknowledge that we're all trying our best and we have the smartest people in the world on our team and there's nothing else that we literally could do. Let's just accept that big programs are always going to be like this. But I don't know how to get there.
You've worked in large established environments, and now you're building one that might become one. What do you miss, and what are you glad you left behind?
I don't think I ever miss anything because I'm kind of obnoxious in a way that I just always look forward. I think the second part of your question is what am I looking forward to? I would say the thing about Gravitics and really the space industry as a whole, it's been great talking with all of you and learning about ESA and how you're starting to come with a new space approach, is that there's this energy. And I've been in the industry now for 20-something years, and I'm being totally honest when I say that industry energy is different. And I know, Chris, you've been in the industry for a while. I'd be curious to get your thoughts too. There's like this palpable excitement. There were all these people, the average age in the Apollo control room launching people to the moon, I think was 28. It's unbelievable. That means that there were people less than 28 that were doing very important things. And then those people turned 30 and 40 and started telling people that they were the experts. And so there's this valley of death between the people who are like 50 and 60 and retiring and this new generation that's coming in. I just happen to be in the middle. And I really, when I talk to the next generation, I think these are the people that are actually going to do the things that we've been talking about for so long. I love the fact that I get to work with these people.